Alright, I'm going to talk about the digital signatures. The concept of digital signatures is basically the same thing as like written signatures. So there are like three main conditions to follow the digital signatures in computing. First is the receiver can verify the identity of the sender. So if you receive a check, like in paper, you know who sends the money to you. And the second one is the sender cannot repudiate the contents of the message. Let's say you send a check for $100 and you want to change to $50. That's the whole point of having a signature, that you cannot change the content as soon as it was sent to the receiver. The third one is kind of the opposite. If you receive a check of $100, you cannot change it to like $100,000. So that's kind of point of having a signature. And in applying symmetric key in cryptography for signatures, in this example we use that the symmetric key uses a shared secret key. If user A receives a message and successfully decrypts that message, the message must have been originated to user B, because only two of them have the secret key. The problem with a symmetric key is that if user C receives that message, there's no way that he cannot prove the message originated from user A or user B. So the solution here is having a public key cryptography, because in public key, every user in the world has its own pair of keys, a private key and the public key. Okay, in this basic concept, the way we read this is that the AND is the message is encrypted using the private key of A, and the output of that is the signature. Once it's encrypted, the user attaches that signature to the message. The way that the receiving end can verify it takes that signature and uses the public key of the sender to decrypt that message. If that message matches the one he sends here, that means the message is authentic and it originated from the real sender. So the problem of this is, if you're going to encrypt a big file like 5 gigabytes, it's not realistic to encrypt big file because it's going to take too long. So the solution here was to use a hash instead. So instead of encrypting the big, like for example DVD file, you just generate a hash of that file instead, and then attach that to the signature. So the way we read this is like from right to left. Generate a hash of that file, encrypt it using the private key of the sender, and then the output S with its signature. Then you send the file attached with the signature to the message. So the way the receiver can verify it is, you receive that signature, you generate the hash, and then you use the private public key of the receiver. If that hash matches with the one you generated, which means that the content of that message is authentic and you know it's received from the user.